Somalia is currently facing one of the worst droughts in decades, driven by the growing impact of climate change. For a nation that depends on rain-fed agriculture, this means disaster. As food production decreases significantly, widespread hunger and malnutrition plagues millions of citizens. As global temperatures rise as a result of anthropogenic climate change and resultant rainfall patterns become unpredictable, large areas of land in Somalia become increasingly barren. Desertification leads to a loss of arable land, making it more difficult for farmers. Droughts deplete water sources, kill crops, and decimate livestock, a cascading chain of destruction.
Rising temperatures, whether it be from burning excess fossil fuels or water overconsumption, accelerate evaporation, leaving barren lands more barren and empty reservoirs more empty. Why should we care about this? Somalia's reliance on agriculture means unpredictable rainfall patterns threaten both livelihoods and ecosystems. Without the seasonal deer rains, crops fail, pastures dry, and millions of people face hunger.
Disrupted ecosystems contribute to biodiversity loss, weakening the natural resilience that keeps the Somali ecosystem balanced. Without intervention, the cascading effects of the drought will eventually ripple across borders.
What if we could source water directly from the air? Fog nets. Our proposed system consists of fog nets made from specialized hydrophilic materials designed to maximize water capture. One particularly effective material is a polypropylene mesh coated with a hydrophilic polymer, which accelerates water condensation by cooling fog to its dew point. From there, the water is directed into underground storage tanks. These tanks can supply drip irrigation systems for agriculture and provide clean drinking water to local communities. This design is inspired by the Namib desert beetle, which climbs on fog-capped desert dunes and uses hydrophilic bumps and hydrophobic valleys on its elytra to extract water from the fog. Similarly, the mesh surface is engineered to mimic this natural design, allowing water droplets to form and roll into collection gutters.
Fog farming supports biodiversity by reversing desertification. Consistent water availability allows native vegetation like Acacia tortilis and Commiphora mira to return, providing food and habitat for primary consumers. Their roots reduce erosion and retain soil nutrients. As vegetation thrives, insects return, boosting pollination and genetic diversity. This initiates secondary succession, restoring ecosystem stability.
The restoration of Somalia's nutrient cycles through fog farming primarily benefits the carbon and nitrogen cycles. As vegetation flourishes as a result of the increased water availability, plants absorb atmospheric carbon dioxide through photosynthesis, incorporating it into their biomass. When leaves and branches decompose, they contribute nutrients like carbon, nitrogen, and phosphorus to the soil, enriching it with carbon-based nutrients and increasing its water retention capacity. Fog farming also supports the nitrogen cycle. Certain native plants, such as the acacia, are nitrogen fixers. Through their symbiotic relationship with nitrogen-fixing rhizobia in root nodules, they convert atmospheric nitrogen into ammonia, a form that plants can absorb and use. This process naturally fertilizes the soil, reducing the need for synthetic fertilizers, which are often environmentally harmful.
We have the power to make a change. Support initiatives that fund fog farming technology and sustainable agriculture, like the German Water Foundation, which has already implemented this in Morocco, Tanzania, Bolivia, and Peru. It may be impossible for one person to make a change, but just like a van der Waals interaction, with the help of many, we can turn fog into life-giving water.